Hello everyone, my name is Dr. Phil Southey and this is a little video on something that I've always found wonderfully unintuitive on why we can't use relative velocities in the Doppler equation. It also gives you an idea of when you have a question like this, you can use the tools at your disposal. I use Excel in this case to try and figure out why things don't work in the way that your intuition might suggest that they should. I'm going to assume that you know what the Doppler equation is. I'm going to assume that you know that when we have a moving source, the sound waves bunch up in front and they spread out behind, as you can see in that image. So here's that Doppler equation, and just a reminder, when we use the plus and minuses, that has to do with whether the observer is moving toward the source, then we use the plus in the numerator. If it's moving away, we use the minus. And if the source is moving toward the observer, we use a minus sign in the denominator. And if the source is moving away from the observer, we use a plus sign in the denominator. Okay, so here's our basic example. We have an observer that's at rest, and we have a source that's moving away from the observer at 10 meters per second. Let's make it nice and easy and say that the source is emitting a sound with a frequency of 1 hertz. And that the speed of sound, remember, is 343 meters per second. So if we use our Doppler equation, the source is moving away, which means that we must use a plus in the denominator. Remember, the speed of the observer is 0. We plug that in, and we find that the frequency has decreased, which is what we expect, yeah, to 0.97167 ... Let's see if I can get that same result if I plug some values into Excel. So I'm just going to define some values here with some quantities. So that's the position. XS is the position of the source. XSO is the distance from the source to the observer. And just so we realize that after every second, the position of the source is going to increase by 10 meters. So if I put that in a table, after every second, I can see here my observer isn't moving, but my source moves 10 meters every second, and therefore the distance between the source and the observer is increasing by 10 meters every second. Very importantly, when the source emits a sound wave, it takes some time for the sound wave to travel. Remember, sound travels at a finite speed, 343 meters per second, and we can calculate the time it takes to travel from the source to the observer simply by taking the distance that the sound travels divided by the velocity or the speed at which it's traveling. And then we can also put another column in here for the time at which the observer receives the sound wave. So if the source emits a sound wave at 1 second, we know that the sound wave will take 0.029 seconds to reach the observer. So relative to the observer, they are only going to receive the sound wave at 1.029 seconds. So if we calculate the length of time that the sound wave will have to travel as the source moves away from the observer, we find that these are the times at which the observer will receive the sound wave. And if you look at the time between these waves, or you could say the crest of the wave, if you want to be more specific, the time between the crest of the wave that the observer receives is this 1.029, showing us that that sound wave has spread out, as it were. And we know that the frequency is 1 over the period. This is the time between crests. We call that time the period. We take 1 over the period and we get the frequency. And as we can see, we get the same result as we got from the formula. So what happens if we now have a similar scenario where the source is traveling at 20 meters per second and the observer is traveling at 10 meters per second? Okay. So according to me, my intuition, this table that we set up is going to remain exactly the same, except that the position of the observer is now changing by 10 meters every second, and the position of the source is changing by 20 meters every second. But everything else seems to me it should stay the same, because the distance between the observer and the source stays the same, the relative distance. and the time it's going to take the sound to travel from the observer, we still know that this sound wave is going to have to travel and reach the observer. That is still going to take some time, so the time at which the observer receives the sound wave will be slightly later than the time at which the source emits the sound wave. But that time between waves should stay the same, and we should have the same frequency. But that's not what we find using the equation. We find that if we say the observer is moving toward, that's a plus, and the source is moving away, that's also a plus in the denominator, we get 0.97245. So close, yes, but not identical. What has happened? So if we're looking at this table, trying to find the error, the thing that needs to change, I would say that it's in this column over here. We have to think very carefully about the position of the observer, because while that sound wave is traveling to the left, in that very small time that it takes to travel to the observer, do you agree that the observer is also traveling to the right? Because it has its own speed. So we have to take account of the fact that in that small time that the sound wave travels, the observer also travels to the right, meaning that the final position or the distance between the source and the observer is not going to be what it was when the observer was at rest. So here's our new table. I've called the initial position of the observer, X observer initial, but I need to now calculate the position of the observer when it receives the sound wave. So if the position of the observer was at 10 meters when the source emitted the sound wave, hopefully you agree that by the time it receives the sound wave, it would have traveled a little bit to the right. So when it receives the sound wave, it's actually going to be at 10.283, etc. meters, right? So the distance from the source to the observer is not going to be that 10 meters. It's now going to be slightly shorter. So the time it takes the sound to travel from the source to the observer is going to be slightly shorter than it was in the previous case. When the observer was at rest, it took 0.029 seconds for the sound to travel all the way back to the observer. But in this case, because the observer has moved slightly, the time it takes the sound to travel from the source to the observer will be slightly less. And if we now work out the time at which the observer receives the sound wave, given this new time that it takes the sound wave to travel to that observer, we find that the time between the wave crests is slightly less than before. Okay. If you want to look into how to calculate this column over here, the distance between the source and the final position of the observer, it's actually a little bit involved. You have to think carefully, so I'll let you work through that if you want. But if we take the frequency, which is 1 over the period of this new time that we've taken between crests, we find that we get exactly the same answer as we got from the from the formula. So once again, the crucial ingredient when we have an observer that's moving is that it moves a little bit in the time that it takes the sound to reach it. And that is why we cannot use relative velocities in the Doppler formula. Thanks for watching.